Hi all, welcome back to another class of our midline. So in today's class, we'll be discussing about few physics under nuclear medicine. So nuclear medicine will be taking class as two sessions. So today we'll discuss few, and the next class we'll discuss half of the nuclear medicine part. So without any delay, I will start the class. I hope my screen is visible. So first we'll talk about the mode of radioactive decay. So beginning to the mode of radioactive decay, we should know what is an atom. So atom is a smallest particle of the substance, so which consists of so many atoms together forms a molecule. So an atom consists of nucleus and electron. In the center, it have nucleus. In the image, you can see center nucleus, which and revolving around is the electrons. So coming to the nucleus part, so nucleus is placed in the center of an atom. So most of all the mass will be concentrated on the nucleus. So this nucleus consists of protons and neutrons. The protons are positively charged. You can see here protons are positively charged, whereas neutrons don't have any charge. So they are neutral. So the mass of this neutron will be equal to the mass of the proton. So going to the electron, so electron they are revolving around the nucleus, so they have negative charge. So this since the nucleus have proton and the neutron, and neutron is chargeless, and proton has positive charge, the nucleus will also show a positive charge. Going to the detail about atomic structure or the atomic, we have something called as atomic number and mass number. So atomic number represents the number of protons in an atom, which is atomic number, whereas mass number is the number of protons and the number of neutron together is the mass number. So in a chemical, A represents the atomic number, sorry, atomic mass, and Z represents the atomic number. A represents mass number, Z represents atomic number, and we write like this. In the symbol, above will be the mass number, below will be the atomic number. So we have something called as isotopes, isobar and all. So isotope is a something which has same atomic number, but the mass number will be different. The atomic number here you can see for the protium, deuterium and tritium, down you can see atomic number is same, whereas mass number is different. So that means there is number of protons will be same, but the number of neutrons will be different. Going to the isobar, in isobar we have same mass number but different atomic number. Here you can see argon, krypton and calcium which have the same mass number 40, whereas the atomic number is changing. Going to the next, which is isotons. So isotons are something which have same number of neutrons, but the number of protons will be different. Here you can see sulfur, chlorine, argon, krypton, calcium consist of 20 neutrons, and the other consist of proton number will be different. Going to the isomer, so isomer have same mass number and atomic number, but they will have different state of excitation. Different state of excitation in the sense the mass number and atomic number will be same. The excitation state they will have low energy, high energy state will be different. So here you can see cobalt which have low energy, and here cobalt M stands for metastable. So it have high energy. So going to the decay, what is decay? So it's an like an unstable nucleus will transform into a stable one by emitting radiation, emitting particles, photons, or even both can be done. So they will release energy in the process. An atom, an unstable nucleus, they won't be stable. So to attain the stability, they will transform into a stable one to attain that, they will emit particles, photons, and all. So basically, we have unstable radioactive nuclei which will be converting into the stable one. So the unstable radioactive nuclei is considered as the parent, and the stable one is considered as the daughter. So if the daughter will also can be radioactive, and they will undergo further decay. So this is radioactive decay is a spontaneous one. They convert mass into energy. So there are different types of decay types. Spontaneous fission is there, alpha decay, beta minus decay, gamma decay, beta plus decay, electron capture, isomeric transition, and internal conversion. So going to the first, which is spontaneous fission. So in this, what happened? We have a heavy nuclei. They will break down into two fragments. So here you can see we have the heavy nuclei. They will break into two fragments in the ratio of 60 is to 40. So not 50 is to 50, 60 is to 40 ratio. So here few neutrons also will be ejected. Neutrons also will be ejected. So the nuclear mass between the two product nuclei will vary according to the process. So here a heavy nuclei will break into two fragments in the 60 to 40 ratio. Along with that, few neutrons, sufficient neutrons also will be ejected. So here the energy which is released will be very large, and that will be around hundreds of mega electron volt. A mega electron volt. So that is the half life. Most of the time, the half life will be for if your the spontaneous fission is done of uranium 235, the half life will be 2 into 10 raised to 17 years, and if it is californium, it will be 55 days. Next, we have alpha decay. So, alpha decay is happening for heavy nuclei like radon, uranium, neptunium, and all. So, in this, what happened? So alpha particle will be a helium ion which have two electrons stripped off. Means an atom will undergo fission, sorry, decay. That time the alpha, whatever byproduct will be a helium which have two protons and two neutrons. So here you can see in this particle which have atomic number and mass number, atomic number Z and mass number A, undergone alpha decay. Daughter nuclei Y have formed, which have and mass number which is sorry atomic number which is Z minus 2 and mass number A minus 4. The kinetic energy of this alpha particle will be almost 4 into 4 and 8 mega electron volt. So here what happen when we undergo alpha decay, the atomic number will be reduced to 2 and the mass number will be reduced by 4. Here you can see minus 2 and minus 4. So here you have an example, uranium 235 and 92 undergone alpha decay, that is thorium 231 and 90 with an alpha particle, or sometimes can be helium. Next is beta minus decay. In this, the neutron in the nucleus, neutron which is present in the nucleus will be converted into proton and electron. So neutron will convert it into proton and electron. So along with that, there will be neutrinos. Along with this, a neutrino also will be ejected from the nucleus. They carry the kinetic energy. So that is called as beta minus particle. So the neutrino is a particle. This neutrino does not have any mass or any charge. So this parent nuclei undergone daughter transformation from the daughter nuclei. So what happened? The atomic number will be increased by 1. So mass number, there won't be any change. So here this carbon is converted into undergone beta minus decay to form nitrogen. Here you can see atomic number have been changed. So this will be always towards the right side because something is increasing, adding to this. So that's why its atomic number is increasing. So it is towards the right side. So the energy will be around 0.156 mega electron volt. So next is gamma decay. So we also call it as beta minus gamma decay or simply as gamma decay. So in this, why it is called beta minus gamma decay? Because so normally an parent nuclei will undergo, here you can see a parent nuclei will undergo beta minus decay. So what happens? after undergoing beta minus decay also, the daughter won't attain stability. They will be still in the metastable state. So to get stability, they will further undergo decay, which is gamma decay, to get the stability. So this sequence is called as gamma decay. So here paranuclear X undergone beta minus decay to form metastable daughter Y. So further they have undergone gamma decay to form stable daughter nuclei. So here there won't be any change in the atomic number. Once after beta decay, whatever beta minus decay, whatever have obtained, there won't be any change in the mass number and atomic number. So here this image you can see here element xenon have undergone so many. It can be twice, two types. One, it depends on the energy. If the xenon undergo B3 beta decay, so then what happened here? It will be around 0.081 mega electron, still in an excited state. So they further undergo gamma 2 decay to form this. Like that, it will. If that is one example. See this arrow mark. If xenon undergo beta minus decay, and this is the energy, there is three chances to form the stability. They can either go one gamma decay or they can go two or three gamma decay. Until like this metastable form a stable one, they will further on keep on undergoing the gamma decay. Next is beta plus decay. So beta plus decay, here what happened? Proton in the nucleus will be converted into neutron and a positively charged electron. In beta minus decay, what happened? The neutron is converted into neutron in the nucleus is converted into proton and an electron. But in beta plus decay, a proton in the nucleus is converted into neutron and a positively charged electron, and an anti-neutron is emitted. In this, what happened? And the parent nuclei will undergo beta plus to get the daughter nuclei. The atomic number will be reduced to 1. They reduce by 1. So here, okay, positron is an antiparticle of an ordinary electron. So after this positron ejected from the nucleus, they will lose its kinetic energy, and what they will do, they will start colliding with the other atom in the surrounding tissue. So what this positron and an electron, they will form an atom, that is positronium. Like when this positron is emitted, so what happened? They will further travel in and they will combine with the other electron, and then they will form positronium. Other chance is that this positron will combine with the negative electron. This positron will combine with the negative electron, and what happened? And process called as annihilation occur. Here what happened? The mass energy is converted into in a linear way. Like this mass energy will be converted for 0.511 mega electron volt, 0.511 mega electron. Equally, it will be converted to two sides. So you can see nearly they will exit in a opposite direction. A positron will combine with an electron, and annihilation process occur. So with equal energy, they will annihilate opposite direction. So this decay is always to the left side, since because of this beta plus decay, we are losing atomic number. So it's always to the left side. Next is electron capture. So electron capture is somewhat similar to the beta minus, not beta plus, similar to the beta minus decay, like inverse to the beta minus decay. In beta minus decay, what happened? Nucleus of neutron of the nucleus is emitting proton and electron. Here, proton and electron and orbiting electron will be captured by the nucleus and will combine with the proton to form a neutron and energy. So in beta minus decay, what happened? The neutron in the nucleus emit proton and electron, whereas in the electron capture, we are capturing the proton in the nucleus will capture an orbiting electron to form the neutron. In this also, in the electron capture also, atomic number will be reducing to 1. So what happened? The neutrino will be emitted from the nucleus. You will have a neutrino which will be emitted from the nucleus, and they will carry some energy. So remaining energy is formed as characteristic X-ray. So usually when if the electron is captured from the K shell electron, then there will be a vacancy formed in the K shell. So that vacancy will be filled by the electron in the L shell. So which will emit an energy, characteristic radiation. So this electron capture is also towards the left side because we are reducing the atomic number. Next we have isomeric transition and internal conversion. So first we'll discuss about isomeric transition. So in isomeric transition, so what happened? There will be an upper excited state element will be there. So here you can see technetium is in the upper excited state. They will be converted into or they will be decaying to form stable one by converting the stability. Metastable one will be converted to stable one. So when this transition is staying for a longer period of time, we call it as metastable state. So next we have internal conversion. So in internal conversion, what happens? The nucleus will decay. Nucleus will decay by transferring energy to orbital electron. This nucleus will start decaying. They will transfer energy to an orbital electron. Then they instead of gamma ray, they will be electron emitted. Nucleus nucleus will sorry nucleus will be what happened decay, they will be converting the energy to orbital electron, and this electron will be emitted, which is called as conversion electron. And what happened, this electrons, now this empty is there, so this empty will be filled by an electron from the L shell to the K shell. So that time what happened, X-rays will be produced. Same. So internal conversion is somewhat similar to beta minus decay. So the main difference is that beta minus decay, the electron originate from the nucleus, whereas in the internal conversion it originate from the electron orbit. And the beta minus particle, they will be emitting continuous spectrum of energy, whereas in the conversion there is discrete, like selected series of energy will be there. So two terms, which is half-life and mean life. Half-life is the time which is required to reduce the activity to one half. So we reduce the activity to half of the initial one. The time taken to reduce the activity of the radiopharmaceutical to half of its original is called as half-life. So it is denoted as T half. Mean life is the average life of a group. So that's about that is about our radioactive decay. So we have learned about alpha decay, spontaneous fission. In spontaneous fission, what happened? Larger nuclei will split into two. Alpha decay, what a dot atomic number -2, mass number -4. And then we have beta minus decay, where nucleus will give proton and electron. My atomic number will be increased by 1. And we have gamma decay. The after beta minus decay, they will, if the daughter nuclide is not stable, they will further undergo decay. And then we have beta plus. The protons in the nucleus will be transferred into neutrons, energy to neutrons and electron, positively charged electron. Here atomic number will be reduced by 1. And we have annihilation reaction. And we have electron capture, opposite of beta minus decay. A proton in the nucleus will capture an orbiting electron to form neutron. Here atomic number will be reduced by 1. And we have isomeric transition, conversion of the metastable to stable one, and internal conversion. Nucleus will transfer energy to orbit the electron, and electron will go from the shell, which is called as conversion electron, and outer shell will fill the inner shell, which produce the X-ray. I hope this what our radioactive decay is clear for you people. So now next we'll go to the production of radionuclide part. How can we produce a radionuclide? So I'll share my screen. I hope my screen is visible. So now we have so many radionuclide, radiopharmaceuticals. So to produce radiopharmaceutical, we require a radionuclide. So how can we produce this radionuclide? So, going to the introduction part, in 1896, Becquerel have discovered the natural radioactivity, which is in the potassium uranyl sulfate. Later on, in the year of 1934, artificial radioactivity was reported or introduced by Marie Curie and Joliet, and they have said that all the atoms which have a atomic number greater than 83, that it is above bismuth, they are radioactive. So radionuclide, they are made by bombarding the nuclei of stable atom with subnuclear particles like neutrons and protons. So they'll collide the stable atom with protons, neutrons to form the radioactive one. So all the radionuclide which we are giving to the patients are artificially produced. So we are today we will be learning how we produce that. So we have cyclotron, nuclear reactor, generator, and all to produce this radiopharmaceutical. So there is three methods to produce this radionuclide. One is reactor produced radionuclide. With the help of some reactor, will produce the radionuclide. Then we have accelerated produced radionuclide, and then we have radionuclide generator. So first we'll go to the reactor produced radionuclide. So before that we should know the fission and fusion. So fission we already learned. So we are splitting a nucleus into two or smaller nucleus fission. Whereas fusion is joining of the smaller two nuclei to a heavier nuclei. That is fusion. So the reactor principle basically works on the fissionable principle. So what we do is we have uranium 235 and uranium 238. These will be used for the reactor principle. So this uranium 235, they will undergo nuclear fission to they will undergo nuclear fission to and split into two or three fission neutrons. So uranium 236 235 will convert to uranium 236. They are unstable and they will undergo nuclear fission. So they will produce krypton and this. Then what happened? Instead of this uncontrolled reaction in nuclear reactor, we control this nuclear reaction. Since this is an uncontrolled reaction, we can control this. So basically, uranium 235 will undergo nuclear fission. So before that, they will be undergoing. Uh, you will get to uranium 236, which is unstable and which will further undergo nuclear fission to form krypton and barium. So the reactor produced radionuclide, we have some equipment is there. So first we have something called as fuel cell. See in this image. So this blue color, you can see blue color, they are fuel cells. So they consist of fissionable material. Okay, this fuel cells consist of the material which we have supposed to undergo fission. Then we have something called as moderator. This orange color one is moderator. So what moderator does is they slow down this fission material, slow down the fission process. So we mostly use moderator as the material we are using in moderator are heavy water or deuterium D2O and graphite. Then we have something called as control rod. This ash color one is control rod. So they are made up of boron and cadmium. So they will shield the fuels. They will protect the fuel cell from one another. From one another, they will protect this control rod. And so when if they are placed incorrectly, if this control rod and this fuel cells are placed incorrectly, what happens? The process or the reactor will melt. So if we are inserting additional control rod, what happens? There will be excess absorption of neutrons. Here you can see what I'll explain you this principle here. So we have other than this fuel cell, moderator, and the control rod, we have coolant in and coolant out to pass the air, and the shielding will be there and the pressure valve. and we have something called as pneumatic line. So we insert the sample through this pneumatic line, and what happened, we'll start the fission process. So once it's not, no, like when the fission starts, this will go up, our control rod will go up, and to switch off this, the control rod will come down. Like that it will be placed. Each nuclear fission event produce more amount of energy, like 200 to 300 mega electron volt. So we can use it for thermal power source. And this, as I said, this pneumatic lines are used to insert the sample. So during this fission, we usually get 99 molybdenum, which is useful for the medical purpose. So we have all this fission product will always have an excess of neutron, that is NZ ratio. Neutron and the Z ratio is more for the uranium 235, and they undergo beta minus particle emission. So whatever radionuclide which is produced through this fission process, we will take it by chemical separation. One method is chemical separation. Second method is using large neutron flux. Like we give large neutron flux to take out the sample. Neutron activation is not required. Next is accelerate. I hope this reactor produced radionuclide is clear for you. Next is accelerator produced radionuclide. By acceleration, by speed, we are producing radionuclide. In this, we have charged particle accelerator. We have an accelerator, the speeding equipment for the charged particle. They accelerate or speed up the charged particle like proton, neutrons, alpha particle, and all. This particle will have very high energy, around 10 to 20 mega electron volt, and we can use Van de Graaff linear accelerator, cyclotrons, and all to give speed or to accelerate. So we are learning about cyclotron. So cyclotron is consist of a pair of hollow semicircular metal electrode. This is a pair of semicircular hollow structure which is made up of metal. They are called as Ds because it's the shape of D, and they will be placed between the poles of the magnet. There will be magnet here, you can see this is your D's, and there will be magnet will be there. Between the magnet will place the D's. So there will be a small gap between this D, and there will be in the center of this gap there will be a point which is called as S, where we keep the ion source, which will keep the thing which we are supposed to produce. So what we do is we give voltage to the, one second. So what happened, we give electricity or voltage to the this D's. That time what happened, there will be a circular path will be there. So what happen is magnetic field is in this direction and electric field is in this direction. So when we give electric field, this sample will start accelerating and it will reach here. When this it reaches here, because of the magnetic field, it will start deviating. So it will go to this side, and when it comes down, because of the voltage, it will come down. And here there is magnetic field, it will go this side. Like that, on each rotation, the voltage will be increasing. Like that, it will start rotating. Orbital rate, this orbital radius increases as the particle uh, follow this spiral path. This orbital radius, this is the radius that will increase as it moves from one D to another D. So when this particles like this, from here it will go front, then come back. Whenever it goes in circular mode, the radius will increase. So at the end, when this they reaches at the end part, there is something called as electrostatic deflector. So this electrostatic deflector will deflect the electrons whatever have been produced to the target. Whatever is produced in the cyclotron will be positively charged particle. So here electrophotic deflector is always negatively charged. They will direct the electrons to the target. So usually gas and liquid targets are used. Solid target will be having contains fluid, and they will be enclosed with a small foil. So we can use oxygen, nitrogen, oxygen at the form of water, nitrogen in the form of gas, oxygen in the form of liquid and nitrogen in the form of gas can be used. So this is what actually happens. It will go the from the source. It will start rotating, and it reaches the deflecting coil and to the target. So the energy of the particle can be calculated then in the cyclotron with an equation which is energy is equal to 4.8 into 10 raised to minus 3 into h into r into z whole square by a. H stands for the magnetic field strength, r stands for the radius, z stands for the atomic number, and e stands for the mass number. So that is about accelerator produced radionuclide. Now we have generator produced radionuclide. So in generator produced radionuclide, we will be having equipment will be there with to hold the parent, so that the daughter will be easily removed from the generator. So there will be a parent daughter nucleate pair in the container. So they will from the parent daughter will be extracted. So mostly we use 99, that is 99 metastable technetium for this purpose. So here you can see the equipment we have. This is the generator. We have eluent and we have eluate and we have aluminum column. So in this there will be 99 molybdenum in the form of molybdenum, that is MOO2 form it will be. They will be bound in the aluminum column. They will be in the aluminum column. So what happened when the saline will be passed through this, they will be elevated, they will be separated. And what happened, daughter which is 99 m per technetium, they can't bind to this aluminum column. So they will be taken out to the eluate like this. And then whatever balance will be 99 m technetium. So that's how we do the generator produced radionuclide. So advantage of this generator produced radionuclide, the 99 m technetium, that is 99 metastable technetium, will emit gamma rays, which can be used for gamma camera, and it have a half life of 6 hours. And the low radiation dose is there for the gamma ray and can be used for so many imaging studies. Disadvantage, this technetium has half short life and we cannot transport this technetium. So that's about our radionuclide production. So basically, we are we have three types. One is radionuclide reactor produced radionuclide, where due to the reactor fission process, this equipment we have to run. And then we have the cyclotron, which is accelerator produced radionuclide. With the help of cyclotron, we are getting the radionuclide. And we have the generator produced radionuclide. Generally, we use this generator produced radionuclide. So I hope that is clear. So next we'll discuss about the radiopharmaceuticals. So till now we learned under nuclear medicine we have learned about modes of radio decay, radioactive decay, production of radionuclide. So next we'll learn about radiopharmaceutical. What is radiopharmaceutical? So we'll see what is radiopharmaceutical, how is main principle, and also called kit. So a radiopharmaceutical is a radioactive material which we are using for the treatment or the therapeutic purpose. So as we say, there is radiopharmaceutical. So they are we also recall this radiopharmaceutical as tracers or radio tracers. So as there in the name, there is something called as radio pharmaceutical, which stands for radionuclide and pharmaceutical. So it's a combination of radioactive nuclide and medicine. So mostly we can use 99 m technetium, iodine 131, thallium 201, iodine 111, fluorine 18, and all as radiopharmaceutical. So main feature of the radiopharmaceutical is that they are easily available and their half-life is very short, and they emit particle and they have high target to non-target activity ratio. Means when this have been given, the image will be more clear in the target area than the non-target area. So before going to that, we should know about the nuclear medicine lab, the where we do this process. So there should not be, first thing we have to take care is the site selection. So there should not be any general public in the area, and it should not be in the residential area and all. And there should not be other X-ray radiation emitting equipment nearby, like we have X-ray unit, CT, fluoroscopy, and all. So those departments should not be near to this unit. And usually this nuclear medicine department should be at the end of the hospital, where general public is less area, and they should have well contact, a well connection between the other department, like tele connection and all should be there. Going to the layout of the nuclear medicine department, so it should have a total area of 150 to 160 square meter, and the walls and the ceiling should be of around 9-inch brick or 6-inch concrete should be used, and there should be fume hood to be installed. Fume hood in the sense, like normally in the olden times in our home and all, we have uh, where we cook food with wood and like wood, and we'll burn it and we'll cook the food. So same for that we have a big, where the our smoke will go up, like that it will be the fume hood. And I'll show you the image, that time it will be more clear for you. And if needed, there should be decontamination room to clean and all. It should be decontamination room, and there should be an active toilet. Active toilet in the sense, the person who had a radiopharmaceutical, for them to wash the face, or for them to go to the toilet and all, there should be an active toilet which should have a shower and wash basin. This is the typical layout for the nuclear medicine department. This will be the entrance. There will be a general waiting area and the reception, and there will be a general toilet for the general public. And this will be the physician or the doctor's room. And this is the passage, 1 mm passage. And here, this is the technologist room. And next to the technologist room, there will be dose administration room, where we give the dose for the patient. Opposite to that, there will be the scan room, where we have SPECT CT system, and then we have the console room. Next, we have hot lab radiopharmacy, where we produce the radiopharmaceutical, and at the end we have the radioactive storage room. This is the decontamination room and the radioactive waste storage room. And opposite, there will be post administration waiting area. After giving the dose to the patient, we take them to this room to sit. We ask them to sit here. We have two, one for the low dose and one for the normal diagnostic level, and for both we have the active toilets. So I hope what like compared to the other department, nuclear medicine, patient will be emitting the radiation. We will give the radiopharmaceutical. Will give dose to the patient. Once radiopharmacy reaches the body, patient will start emitting the radiation. So this the system and all is of no problem. If patient should not be in contact with the general waiting area. So ventilation, there should be proper ventilation for the airflow. It should be from the low activity to medium to high activity area, and there should be air condition should be so comfortable for the patient. And in the room or in the nuclear medicine, there should be generator, which we discussed. Generator to produce the radiopharmaceutical, and there should be a dose calibrator. I'll explain you what is dose calibrator. Then we have the contamination monitor to check how much radiation dose is there, and we have fume hood and centrifuge L bench. I'll explain this thing. So generator, as I said, we have this um, the produce the radiopharmaceutical. From the molybdenum will go get we get technetium, and they have wet system, dry system, and all. So the dry generator, there will be specific amount of saline which is placed in the generator entry port. There will be like this. Whereas in the wet generator, there will be saline reservoir a little bit away. So dose calibrator, which is equipment where we keep the radioactive isotope or the radiopharmaceutical inside, and will measure how much is the dose. Contamination monitor is GM counter. We'll take this. This is the GM counter. So when we reach the near the radiation zone, will detect. It will start showing the reading, and also sometimes there will be audible system. They'll make sound. This is the fume hood where we do our process. There will be, we'll do like this, and whatever fume will be going up. So they are used to protect the user from the inhaling of the toxic gas. We are making toxic gas, so to reduce this inhalation of this toxic gas and to protect the environment, protect the product of the experiment, and then we can prevent the explosion, spill contamination, spillage of the on the floor, and other necessary things can be reduced. This fume hood is made up of lead. The centrifuge, I think it's which we have learned in microbiology, biochemistry, and all. So they have a centrifugal force like rotational speed, which will be very fast. So they will mix the equipment. So this spin will keep the equipment, and with the spinning wheel, and they will spin so that we get the sustainable dose for the patient. L bench is this kind of L shield. So they are designed so that the user will be protected. So we can stand here and we can do the procedure like this. And it is made up of 4.8 gram per centimeter density lead, and they will be painted with high glass paint, epoxy paint, so that we can clean it easily. So this basic concept is that our nuclear medicine study, once a radio pharmacy or radio tracer is injected, we will start measuring the function of this radio pharmacy in our body. So in our body, different body part have different biological function. So that will be found out, and we'll draw graph. We can see like this, and we'll get the graphical representation also. Going to the tracer and the compartment. So tracer is a substance which follow the biological process. That means they follow or they traces the biological process or the physiological process. They are also called as labeled radionuclides. And the main property is that they trace the physiological process. They find out what is the physiological detail, and how much mass. If we are giving more amount of radio tracer, it should not alter the physiological process, and small amount of tracer is enough to give more in detail, and there should not be this isotope effect is negligible or less quantitatively predictable. So tracer will give injected into the body, and we take some images of its pathway, and it from the capillary, from the blood vessel through the capillary, it will go to the tissue and to the specific structures. So there is two mechanism for the transport of substance. One is active transport, second one is passive transport. So going to the active transport like energy required to move substance, again concentration, like opposite to the flow, and the passive transport, same direction of the concentration gradient. So high target to non-target ratio. So this is like activity. We say it based on the activity. So when we give the pharmaceutical, there will be areas of high target, means more area, clear image, and there will be area where there is no radio pharmaceutical. The ratio between these two is called as high target to non-target ratio. If there is more area where the radio pharmaceutical is seen, then we can say we have high target to non-target ratio. And if there is less high target area seen, we can say we have low high target to non-target activity ratio. Production we have already discussed, so I am not explaining again. We have 99 technician labeled radiopharmaceutical, which will be produced by the generator. So we have number of called kit to produce this. So what is called kit? So called kit is a packet which consists of different ingredients which will be used to produce the radiopharmaceutical. So they are in a freeze dried. We'll freeze it and make it in a dried form so that it have a long half shelf life. We can store it for a long period of time. So it's from several months to years. So it will be like we store it in the refrigerator for 2 to 8 degrees Celsius. This cold kit consists of so many ingredients to make the radiopharmaceutical. So main ingredients of the cold kit is the ligand, which is the active ingredient. We also call it as complexing agent, and we have reductant, which is reducing agent, and we have antioxidants, buffer, and some miscellaneous compounds. Going to the ligand, they form complex with the metal. They will be joining us, make as a complex method, complex formation will be there. So they can be like monodendritic, like single connection, or by two connection like bidendate or polydendate, several connection. Depends upon the groups they are available. So example is HIDA and MDP. The radiopharmaceutical example is HIDA and MDP. Reductant, they are also called as reducing agent. They will lower the oxidation state. If the oxidation state is more, there will be more precipitation. So to reduce that, we use reductants. So stannous salt are used as the reductants. They are water soluble at very low pH. They are stable, they are low toxic, and it's good effective. They are effective in the room temperature also. Some example of the stannous salts are stannous chloride, stannous fluoride, stannous citrate, stannous phosphate, and ascorbic acid. Next, we have antioxidants. So, antioxidants when there is a presence or when we have more amount of oxygen, what happens? There will be moisture in the area. So, this moisture will uh, they cause damage to the colic itself. So to reduce that, we have antioxidant to give more stability. So we use ascorbic acid and aminobenzoic acid as antioxidants. Then we have buffer. So buffer makes complex formation and they change the distribution, how this radiopharmaceutical goes through our body, and they will increase the shelf life and the stability of the kit, and they maintain the pH. So miscellaneous compounds are like catalyst, accelerator, solubilizing agent, stabilizing agent, additives and preservatives, and filters. So going to the procedure, I mean how you make the call kit. So first we have to take the appropriate kit, like to produce which each radiopharmaceutical. For example, we have MDP, DMSA. So for each one there will be specific kit, and we have to calculate how much amount of technetium have to be volume is required, and we require a kit, that is the which kit and the radionuclide, this technetium 99, syringe, needle, shielding for the syringe, swab, and all have to be taken. And this kit, we have to make this kit according to the manufacturing. That kit, there will be manufacturing instruction, we have to make according to that. And after that, we have to label. We in that radiopharmaceutical, we have to label how much is the radioactivity, time of when we have made it, date of when we have made it, volume, expiry date, time, and all, whatever instruction, all have to be labeled, and we have to record all the procedure. After that, we have to store according to the manufacturer, how manufacturer have said, accordingly we'll store the radiopharmaceutical. So advantage of this call kit is like we can easily make it, it's readily available, and for the operator we have low radiation hazard to the operator, and we can use sterile products, and they are sterile, and they are stable, and it's possible for the diagnosis, and they are readily available. So that's all about radiopharmaceutical. So we learned about what is radiopharmaceutical and layout of the nuclear medicine, hence fume hood, centrifuge, L bench, and this transport, high target and on-target ratio, then called kit, components of called kit, and how we make the called kit. I think my screen was not visible. Okay, I'll just show you again. Okay, what to be shown, I'll say this is the layout. One second. Okay, this is the layout of this nuclear medicine. This is what I hope you have seen. If not, I'm showing again. We have the general waiting area, reception, toilet, physician room is there where we do the scan, and we have technologist room where the dose administration, where we give the dose to the patient. Hot lab is there where we make the radiopharmaceutical. Decontamination room, waste storage room, source area, and after giving the radiopharmaceutical where we sit the patient, and this low normal, and this is with low dose, and the active toilet. If you have not seen the images, I'll show you once more. This is fume hood, this is L bench. Yeah, other if even though you have not seen the slide, it's okay. I have nothing much is there. I mean, no, nothing, images are not there. Only the contents were was being shown. Okay, so going to the last part of the today's class, one more topic we'll learn today. Okay, so today we'll learn one more thing, which is wipe testing, contamination monitor, and isotope calibrator. So going to the first, which is wipe testing. So wipe test is done to see if there is a small amount of radioactive contamination in the bench top and all. Like if it is there is small contamination in the shipping package, all we do this wipe test. We'll actually wipe the surface with alcohol soap patch or like cotton, and we'll measure how much is there. So for that, before performing, we require protective attire like lab coat, eye protection, gloves have to be worn, and we have to gather equipments like cotton swab, filter paper or paper towel have to be taken, and vials or envelopes have to be taken. I think my sound was not audible for you people. So we were talking about the wipe test. So wipe test, we have the like we have to clean the area. So we'll clean the area, and then what we do, we'll find out the decontamination part. So we have this protective attires, lab coat, eye protection gloves, cotton swab, and all. And what we do is we take the swab from the different areas within the lab, and one wipe is required from storage area also. If we are not stored for some period of time, we can mention that it's no use of storage or for this many period of time, and we have to place this in separate vials, and we have to mention the location, and the laboratory wipe test report have to be filled. We have to take sample in S-shaped motion, like S-shaped motion. We have to take the sample, and this we also can use chem wipes. This is chem wipes, and all the cotton swab will have a cut stick. Stick will be there. We have to cut the stick after putting it into the vial, and we have to close the vial lid. And this samples then we'll place in this an Eppendorf tube. This is the Eppendorf tube. We'll place it in the Eppendorf tube. We'll mix with the cocktail, and then we'll close it. So along with the area, we take one background Eppendorf, that is the empty Eppendorf tube also will be placed, and then we'll keep it in the vial holder. We'll keep it in the vial holder. After that, we load it in the LSC, that is liquid scintillation crystal, and we'll do the wipe test, and reading will be shown. So we have to fill the report. You should have the information like who is the user, which place have done, date, building or room number, who have done the wipe test, and the diagram of this needed. Going to the contamination calculation, to calculate the area, the contaminated area should have a dose which is more than the 3 times of the background count. We have kept an Eppendorf without any sample, so it should be the contaminated area should be more than that background count into 3. So if it is more than that, then the area is contaminated. Contamination in monitor is done by the GM counter. So main GM counter under detector part I'll explain in detail. Then we have isotope calibrator. So they are mainly ionization chamber. So they measure the radioactivity of the radiopharmaceutical. When this radiation is passed through this, what happened? Ion pair is formed. So they are separated by the electronic voltage. Like here, when we give high voltage to this metal, into the cylinder. So when we keep the sample like this, we'll keep the sample inside, so the radiation is emitting. So that time what happened, there will be air inside this, so that what ion pair will be formed. So positive ions will go to the negative electrode, and the negative ion will travel to the positive electrode with the cylinder. So this cylinder will act as the cathode, which attracts the positively charged, and that will be read by the current amplification and will be displayed. So this ionization current will be proportional to the activity of the sample. So we measure it for a measure dose of the radiopharmaceutical, and we require this. There is more shielding. Proper coverage is required. We have to seal the isotope calibrator properly, and we require a normal lead shielding also is needed. Okay, that's all for today's class. If there is any doubt in the class, any clarification is needed, we'll be discussing in the tomorrow's class, next class. So I mentioned what all doubt is there. That's all for today's class. Thank you.